Hi. Today I would like to talk about atoms, elements, and ions. And a big part of this is really to talk a bit about the periodic table. We're not going to learn the entire periodic table in this lecture or even in this course, but I do want you to become familiar with some of the more common elements that occur in minerals, where they occur in the periodic table, and consequently what kind of charges they're likely to take. So today we will talk about the terms that we use to describe atoms and ions and electron configurations. That's really most of the lecture. I do want to touch on charge balance, and I also want to touch on the most common elements in the crust and mantle. At the end of this lecture, I hope that you would be able to use terms correctly for atoms and ions, use the periodic table to predict electron configurations, really likely charges for ions, to be able to balance compounds, especially for minerals, by using the periodic table, and then to recognize the more common elements in the crust and mantle and be able to predict the likely abundances of certain types of minerals. For example, there are lots of silicates because there's lots of silicon in the world. There's not very many germanates because there's not very much germanium in the world. So atomic terminology. The term atom comes from a root word that means indivisible, but in fact we know that atoms are divisible because they consist of electrons, which have a negative charge. This little dash apostrophe VE is negative. Protons have a positive charge. They're in the nucleus, so we use this term positive. And neutrons have no charge. And as we've talked about in previous lectures, most of the mass is contained in protons and neutrons. Now, each atom of an element has the same number of protons, but different isotopes of the same element can have different numbers of neutrons. So for example, oxygen is element number 8, so it has 8 protons and 8 electrons in its neutral state. It has 3 stable isotopes, 16, 17, and 18, corresponding with 8, 9, and 10 neutrons. Almost all of it is oxygen 16, that's 99.8%. Most of the rest is actually oxygen 18.2%, and there's a little bit of oxygen 17.05%. It's also possible to have unstable or radioactive isotopes. Tritium, hydrogen-3, is an example. It decays to form helium-3, and we can see that it's unstable if we look at the mass. The mass of hydrogen-3 is greater than the mass of helium-3. So hydrogen-3 can convert to helium-3 plus energy. And to remind you, the convention for isotopes, we have the atomic symbol is the letter or letters here. The lower left is the proton number or the atomic number, and the upper left is the sum of protons and neutrons. So just to have a little review question, when would we say an element has multiple isotopes? When Z is the same, but the number of neutrons is different. When Z is the same, but the number of protons is different. When Z is the same, but the number of electrons is different. Or when it is radioactive. And the answer is when Z is the same, but the number of neutrons is different. Z is the atomic number. It's the number of protons. So every specific element, oxygen, chlorine, iron, whatever, each of those elements has the same number, each atom has the same number of protons, but different isotopes will have a different number of neutrons. And whether an element is, or isotope is radioactive says nothing about whether it has one or more isotopes. So at this point, especially in the context of the first lecture in this series, I hope that you'd be able to understand and work with atomic and isotopic notation. So now let's talk about electron shell occupancy. There are more complex models of how electrons are distributed around nuclei, but the Bohr model of an atom is generally sufficient for the purposes of most of what we do in earth sciences. The concept here is that electrons occupy certain regions around nuclei called shells. The innermost shell has 2 electrons, so it's labeled number 1, or by convention it's called the K shell. The next shell has 8 electrons, and that's shell number 2, it's called the L shell. The next one also has 8 electrons, shell number 3, quantum number 3, labeled the M shell. The next one has 18 for the N shell, and it goes up from there. So the concept is that electrons occupy shells. These correspond to the first quantum number, n equals 1, 2, 3, and so on. The other component that we need to discuss is the concept of a subshell. The subshell is the second quantum number. These are particular types of orbitals. So this second quantum number, the subshells are referred to as S, P, D, and F. So we might talk about the 1s subshell. For shell 2, there are two subshells. There's the 2s subshell, which has 2 electrons, and the 2p subshell that has 6 electrons. In general, this is how the shells and subshells are distributed as we move up in atomic number. So the first shell has only the s subshell, 2 electrons. The second one has the s and p subshells. The third one has the s, p, and d subshells, and so on and so on. The way that these shells are filled as we move up in atomic number follows this pattern. The first, we fill the 1s subshell, then we fill the 2s subshell and the 2p subshell, then 3s, 3p, 4s. And this is the tricky part. After we hit the 4s subshell, the next subshells that are filled are the 3d subshells, then the 4p subshells. So if we look at this distribution of the different subshells as we move from shells 1 through 7, the fill order follows this set of arrows. So we fill 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on, and so on, and so on. So if you write out the shells and the subshells in this form, and you remember this sequence of arrows, you can figure out how the fill order works. If we look at a specific element, here's titanium, atomic number 22, so 22 electrons. Those would be filled in this order: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we backtrack to 3d2. That's this backtrack right here from 3p, 4s to 3d. So if you write out this description of shells and subshells, then you should be able to predict how adding or subtracting an electron to an atom will affect the occupancy of its electron shells. I know I went through that very quickly, but if you go back and review this, I think you'll see how this all works. Now let's talk about the periodic table. The periodic table is organized according to how the different shells are filled. So if we look at the first row here corresponds to the filling of the 1s shell. The second row corresponds to filling of the 2s shell and then the 2p shell. Third row is the third shell. Fourth row is the fourth shell. Fifth row is the fifth shell. What makes this a little weird with respect to subshells is that when we look at row 4, if you remember that fill order, 4s, the next subshell that we fill is 3d. So we do 4s, then we fill in a whole bunch of 3d electrons before we start filling the 4p electrons. And similarly here, row 5 has a whole bunch of 4d subshell electrons in here. And it gets even more complicated as we come down to 6 and 7 because we jump to the lanthanides and the actinides, which have an f subshell in here. We're not really going to deal with those in this class, though. Thank goodness. So second row, we fill 2s, then 2p. Third row, we fill 3s and then 3p. And then fourth row, we fill the 4s and then that strange 3d and then 4p. Now there's another quantum number that we can consider. The third quantum number says that electrons have spin. Now what that means is that electrons are paired. The spin quantum number tells you which way the electron is spinning. In this orientation, with the plus 1/2, it's spinning in this direction. With the minus 1/2, it's spinning in this direction. There's a rule called Hund's rule that says that electrons enter suborbitals with the same quantum number first. I'll show you what that means, but basically what it means is that electrons all want to spin in the same direction if they can as they fill up shells. And then after they've filled as many with the same spin, then they start adding in electrons with a different spin number. This turns out to be important for understanding magnetism. So let's just work our way through the periodic table and see how different shells are filled. So here's hydrogen. It has only one electron, which goes into the 1s2 subshell. And for helium, now we have one electron that has one spin direction, a second electron that has the opposite spin direction. This fills this shell. And as a consequence, this atom is extremely stable. It doesn't want to gain or lose electrons. That's why helium is a noble gas. It's very, very unreactive. As we move to lithium, atomic number 3, the inner 1s shell is already filled. So the third electron goes into the 2s2 suborbital, and it has this spin direction. When we go to beryllium, the second electron goes into the s2 subshell and it has the opposite spin direction. Okay, so this doesn't seem very complicated, but where it starts to get a little tricky is when we start looking at higher atomic numbers. So boron, the 5th electron goes in this location, and the 6th electron jumps over here. These two have the same spin direction. Okay, so we don't fill in an opposite spin direction in this location. Rather, we add an electron with the same spin orientation. This is what Hund's rule is all about. 7th for nitrogen goes here, and then the 8th with oxygen will start to fill in electrons with a different spin direction. So here's number 8, here's number 9, and here's number 10. When we get to 10, neon, both the 1 and the 2 shells are filled. And so neon, like helium, is very unreactive. And we can refer to this as a neon core. All the larger atoms with more electrons and protons will have this neon core, and all of the other electrons are added on top of that. So here's a quick question. What is the correct electron configuration for aluminum 27? And the answer is B. So first of all, you want to add up the number of electrons here. It should be 13. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and 1 is 13. And these are filled in the correct order. It goes 1s2, fills that, fills the 2s2 and the 2p6, the second shell, completely, fills the s shell, subshell of the third orbital, and then starts filling the p orbital. And if you go back and look at aluminum, then you'll see that this is the configuration. Again, I went through this very quickly, but I hope that you'd be able to go back to the periodic table, look at the way that the electrons fill into different shells, and be able to infer electron configurations. Now let's talk about ions, because that's really what we deal with most in the earth sciences. In general, atoms want to have completely filled or empty electron shells. We refer to valence electrons, and these are the electrons that can participate in the formation of a chemical bond, either ionic, they can give or take an electron, or covalent bonds where they can share an electron. We'll talk more about bonds in a later lecture. Valence is normally determined by, well, there's a couple of different ways of thinking about this. The number of electrons in energetically similar suborbitals, the number of electrons in excess of a noble gas core, this is actually how I think about it, or the column number. So am I in column 1 or 2 or 6 or 7 on the periodic table? This doesn't work very well for transition elements, so these are the ones that are in the middle of the periodic table, but it works very well for the elements that are on the left-hand side of the periodic table and the right-hand side of the periodic table. And fortunately, that's where most of the elements that we deal with in the earth sciences fall. Okay, so like I said, here's column number. These are fairly easy to predict. These are fairly easy to predict. These are not very easy to predict. So let's look at this and count up the number of valence electrons for different types of atoms. Let's start with lithium. Lithium's pretty simple. It has a filled first shell, so this would be the helium core, and it has a single electron in its second orbital. So lithium has one valence electron. Nitrogen also has a filled helium core. The first shell is completely filled, and it has 1, 2, 3, 4, 5 electrons in its second shell, so it has 5 valence electrons. If we look at sodium, the first and second shells are filled. It has a neon core. It has a single electron in its outer shell, so it has a single valence electron. So now let's look at fluorine. Fluorine sits over here. It's in the 7th column. How many valence electrons do you think fluorine has? The answer here is 7. If we compare fluorine to nitrogen, we would see that fluorine has 2 more electrons, 1, 2, and if we counted up the electrons in shell 2, we would find that it would have 7. So at this point, I hope you'd be able to use the periodic table to infer likely ionic charges for some common elements. Now, charge balance. I use charge balance all the time in determining mineral formulas and thinking about reactions and mineral chemistry. So consider oxygen and magnesium. So oxygen sits over here. Oxygen has 6 valence electrons. It has a helium core plus 2s2 and 2p4. Magnesium has a neon core plus 2s2 valence electrons. In general, magnesium would like to lose 2 electrons so that it empties out its outer shell, while oxygen would like to gain 2 electrons so that it would fill its outermost shell. As a consequence, elements like magnesium and oxygen would like to gain, lose, or share electrons through a chemical bond. And in general, magnesium would like to lose these 2 electrons, and oxygen would like to gain these 2 electrons. The gain or loss of electrons lead to a net charge. So oxygen always has a net charge of -2, and magnesium always has a net charge of +2. The way that these ions combine is not random, and this is the key point. The charges have to balance. So if magnesium is +2 and oxygen is -2, the compound magnesium oxide is stable. Mg2O is not stable. 2 times +2 is +4, -2 is still +2. And compounds, stable compounds, cannot have a net charge, either positive or negative. Now, when atoms gain or lose an electron, they're referred to as ions. So a positive ion is called a cation, and a negative ion is called an anion. The common elements that we deal with are shown in these gray boxes here, and some other ones that are important are shown in the red boxes, but they're a little complicated, so I'll come back to these. These are in the first column. Hydrogen, sodium, and potassium in geological materials take a charge of +1, magnesium and calcium of +2. As we work our way across here, aluminum +3 loses 3 electrons, silicon +4, phosphorus +5. When we look at these atoms over here, oxygen is -2, fluorine is -1, and chlorine is -1. The unusual ones are sulfur and iron. So sulfur has 6 electrons in its outer shell. So it has 2 choices. It could lose 6 electrons, adopt a charge of +6, and it does that, and it bonds with oxygen to make sulfates. or it can gain 2 electrons and adopt a charge of -2, and in that case it forms the sulfides. So sulfur goes either way. It can be a cation or it could be an anion, and when it forms a cation, it forms a whole class of compounds that's different than the class of compounds that form when it has a charge of -2. Iron, these transition metals, they can adopt a range of charges. That you see this all the time in chemistry. In general, in the earth sciences, these tend to have a limited range of charges. They're almost always either +2 or +3, although these over here actually can take +4. But iron in particular takes 2 very common valence states as either +2 or +3. The blue boxes here, these are the elements that are the most common. The green boxes are elements that are of interest geologically. And you can see that most of these, like I've said before, fall to the right in the periodic table or the left in the periodic table. These are of economic importance, these transition metals. Lead is very important, not just economically, but for geochronology, which is why I've put thorium and uranium in here as well. The charges on these elements in particular is a little bit difficult to predict based on the periodic table, and so I just learned those. The rest of these are pretty straightforward to predict from the periodic table. So again, the charges have to balance. So let's take a really complicated mineral like muscovite, potassium aluminum silicate with some hydroxyl associated with it. If we look at all the cations, so this is potassium, aluminum, silicon, and hydrogen. Hydrogen and potassium both have a charge of +1, so 1 potassium is 1, 2 hydrogens is 2. Aluminum sitting over here, column 3, has a charge of +3, so 3 aluminums, charge of +9. Silicon, column 4, always +4, so 3 silicons, a charge of +12. We add up all this together and we get a charge of +24. How many oxygens do we have? Well, there's 10 here, +2 here is 12. Oxygen is always -2. 12 times -2 is -24. We add these two together, the sum of the cation charge and the anion charge, and they sum to 0. So it charge balances. So here's a question. Is this compound, magnesium silicate with hydroxyl, is that charge balanced? The answer is no. If you add up the negative charges, you'll find they exceed the positive charges. But this compound, if you had another magnesium in this composition, then the charges would balance. In fact, this is the mineral talc. So at this point, I hope you'd be able to work with atomic and isotopic notation and terminology, have some facility with how electrons enter and leave electron shells, be able to use the periodic table to infer electron configurations, also use the periodic table to infer likely ionic charges, and then demonstrate or calculate charge balance. All right, thanks very much.